Good morning, students. Today, let's start with next concept, partition. So this you have learnt in BSc 5th semester. So here, let A comma B be a closed interval. Partition of closed interval A comma B means a finite set of points P which consists of x0, x1, x2, etc. up to xn, where these points lie in between this number A and B, or these points belong to this closed interval A comma B. So here in this partition we are choosing finite points from this interval, and you know this interval consists of infinite points, but we are choosing only finite points from this interval and naming that as P. I am naming that set as P. And here, this first element should be this A. And the last element should be equal to B. And here, like this, you can choose number of partitions. Okay, and here in this partition we have n plus 1 elements. So here is x0, x1, etc. up to xn. So from x1 to xn you have n points and this x0. So it is totally, this P consists of n plus 1 points. Clearly, any number of partitions of closed interval A comma B can be considered. So you can consider number of partitions. So there are many partitions for this. See, I will just show you an example. Let me have first partition. I'll name that as P1. And you can choose that as 1, 3, 5, 9, 10, like this. And P2 you can choose this as 1, 2, 4, 6, 8, 10, like this. So you can also choose 1, 1.5, 2, 2.5, 3, 3.5, so etc. up to 9.5, 10. So here, like this, you can choose many partitions. So this is not only 3 partitions you can choose. You still have many options. Okay. See here, these are the subintervals. Subintervals of closed interval A comma B. See, with that points x0, x1, x2, x3, etc. up to xn, I have made a subintervals. I have taken closed interval x0, x1, x1, x2, etc. up to xi minus 1, xi, where xi is in between this x0, x1, x2, etc. up to xi, etc. up to xn. Means xi is the intermediate point. Okay. So and etc. up to xn minus 1, xn. So these are all the subintervals of closed interval A, B. We shall use the symbol delta xi to denote the length. See here, delta xi is the length between these 2 points. See, if you take delta x1, then that will be the length between these 2 points. Delta x2 will be the length between these 2 points. So, in general, delta xi denote the length between these 2 points. Okay. So, this is the length xi minus 1, and it is of ith subinterval. So, here, let f be a bounded real function, and we have already learnt what bounded function is. So let f be such function on closed interval A, B. If f is bounded on this closed interval a comma b, then obviously it will be bounded on each subinterval of this. Okay, that is the obvious thing. And here let small mi and capital Mi be the bounds, means infimum and supremum. So this is the greatest lower bound and this is the least upper bound, okay, of f in delta xi. See here, this means mi and capital Mi are actually infimum and supremum in this particular interval. If you take m1 and capital M1, that will be the infimum and supremum in this interval. And similarly, M2 and capital M2 will be infimum and supremum in this interval. See, and etc. Okay. So, here in general, we are considering Mi and capital Mi be the bounds in this interval. Okay. So, here, see, it is telling that is Mi is the supremum of f of x in this particular interval where x is in between xi minus 1 and xi. And this small mi is the infimum of f of x in this interval. Okay, so here we are considering this interval. What is that? xi minus 1 comma xi. So in this particular interval, this is the infimum of f of x and this capital Mi is the supremum of f of x. Okay, so here Mi is the supremum of f in ith subinterval and small mi is the infimum of f in ith subinterval. Okay, so now let's move on to Riemann Stieltjes integral definition. So what is actually the difference between Riemann Stieltjes integral and Riemann integral? Actually, Riemann Stieltjes integral is a generalization of Riemann integral. See, where instead of integrating with respect to a variable, we integrate with respect to a function. Okay, see, this allows us to consider more complex integrals that can be useful in various areas like probability theory, stochastic processes and functional analysis and so on. Okay, see, let alpha from closed interval a comma b to r real numbers be a monotonically increasing function and small f, that is function f from a closed interval a comma b to r be a bounded function. So you know what is monotonically increasing function and also you know what is bounded function. Then there is a generalization of Riemann integral known as Riemann Stieltjes integral. Okay, see here this in Riemann Stieltjes integral, the general form, see, it will be like this: integral a to b of x d alpha of x. Okay, this is Riemann Stieltjes integral. Okay, and here integral a to b f of x dx, f of x dx is Riemann integral. Okay, so this is the difference between Riemann Stieltjes integral and Riemann integral. See here, this is integrating with respect to a variable and this is we are integrating with respect to a function. Okay, this is just x and this is a function of x. Okay, so this is the difference between Riemann integral and Riemann Stieltjes integral. Okay, fine. So here we considered delta alpha I, this alpha of xi minus alpha of xi minus 1. So we are considering this instead of delta xi. There in Riemann integral we had this delta xi is equal to xi minus 1 in Riemann integrable, and here in Riemann Stieltjes it is delta alpha I equal to alpha xi minus 1. So it should be noted that Riemann integration is a special case of Riemann Stieltjes integral. Okay. So now next we'll move on to the definition of upper sum and lower sum. Okay. See the upper sum of f with respect to alpha and with respect to the partition p is defined by u of p comma f comma alpha, which is equal to summation of I equal to 1 to n capital Mi delta alpha I. So here this you know what is Mi. It is the supremum of the interval xi minus 1 comma xi, closed interval xi minus 1 comma xi, and this delta alpha I is alpha of xi minus alpha of xi minus 1. So, and you here you are summing up all m1 m2 etc. Okay, so here you are doing that for I equal to 1 to n. So you are summing up all these from 1 to n. Similarly, the lower sum of f with respect to alpha and with respect to the partition. See, with respect to the partition p means it will change for each and every partition. You if you take p1 for u of p1 comma f comma alpha, you have one number, and for another partition if you consider, you have another value for p2. So similarly, the lower sum of f with respect to alpha and with respect to partition p is defined by L of p comma f comma alpha equal to summation I equal to 1 to n small mi into delta alpha I. See, here we have supremum and here we have infimum. Okay, that's it. And also note that if small m and capital M are lower and upper bounds of f on closed interval a comma b, then we have m less than or equal to small mi less than or equal to capital Mi, and that is less than or equal to capital M. See, this is obvious thing. See here. See, if you have a comma b, and for this a comma b, small m and capital M is the infimum and supremum. Okay, infimum and supremum. And now what you are doing, you are dividing this interval now. So you are having x0 comma x1. See, this is nothing but a, and x1 comma x2, and so on etc. up to xn minus 1 comma xn, where this is b. Okay. So here for this whole closed interval a comma b, small m and capital M is the infimum and supremum. So here, if you take the next interval, so obviously the infimum will be greater than this interval. If you consider this interval only, then that infimum will be equal to this a. So that is equal to this m. So if you consider the last interval, then that capital Mi will be equal to this capital M. So that is the obvious thing. And here this inequality holds. M less than or equal to Mi less than or equal to capital Mi less than or equal to M. So when you multiply throughout by delta alpha I, you get this. M into delta alpha I less than or equal to Mi into delta alpha I less than or equal to capital Mi into delta alpha I less than or equal to capital M into delta alpha I. And if you take summation throughout, see here we have taken summation here because we don't have any I here. So this M has nothing to do with this summation. So I have just written it outside. Okay, and summation I equal to 1 to n. And here I have not done like that because this consists of I here. So the summation is for both Mi as well as delta alpha I. So similarly, I have taken the summation I equal to 1 to n for these two also. So here we have, first we'll compute what is this summation I equal to 1 to n delta alpha I is. Okay, See here, because this is nothing but lower sum, this is nothing but upper sum. Okay, so let's compute what is this. Okay, so here summation I equal to 1 to n delta alpha I. If you put I equal to 1 to n, we have delta alpha 1 plus delta alpha 2 plus etc. up to delta alpha n. Okay, delta alpha n. So here, what is this delta alpha 1? Actually, it is alpha x1 minus alpha x0, because I have told you delta alpha I is equal to alpha xi minus alpha xi minus 1. So your delta alpha 1 will be alpha x1 minus alpha x0. Similarly, delta alpha 2 will be alpha x2 minus alpha x1. So similarly, up to this, see, delta alpha n will be alpha xn minus alpha xn minus 1. And here, this alpha x1 will get cancelled with this minus alpha x1. And similarly, alpha x2 will get cancelled with the next term, alpha x3 minus alpha x2. And similarly, this alpha xn minus alpha xn minus 1 will also get cancelled with the previous term. So finally, you will be left with alpha xn, this one, and minus alpha x0, this term. And what is this actually? Xn is nothing but b, and x0 is nothing but a. See that closed interval a comma b. Okay, here this is nothing but x0, and this is nothing but xn. And this x0 equal to a and xn equal to b holds for each and every partition which you consider. Okay, so alpha b minus alpha a. So I am using this value of summation I equal to 1 to n delta alpha I here in this equation 1. So finally I will have m into alpha b minus alpha a, m into alpha b minus alpha a less than or equal to lower sum, less than or equal to upper sum, and that is less than or equal to capital M into alpha b minus alpha a. Okay. See here, you have some points to note down. First one, u of p comma f comma alpha, upper sum and lower sum. This one, the u of p comma f comma alpha and l of p comma f comma alpha are called upper Riemann sum also. Instead of upper sum, you can call upper Riemann sum. Or instead of lower sum, you can call it as lower Riemann sum. Okay. And second one, as the number of elements in partition increases, this upper sum decreases and lower sum increases. So you can take any example and try. Say the example 1 comma 10, closed interval 1 comma 10. In that only, you can. I have this. Okay. See, in this example, closed interval 1 comma 10, actually I have 3 partitions here, and in this 3 partition you have actually 5 elements here and 6 elements here, and you will be having more elements here, more than 6 elements. So as and when the number of elements increases in the partition, upper sum decreases. So you can check for each and every, you can just check for p1 and p2. Okay, you will have this result. U of p comma f comma alpha decreases and L of p comma f comma alpha increases. Now let's define upper Riemann Stieltjes integral and lower Riemann Stieltjes integral. Okay, let f from closed interval a comma b to r be a bounded function and alpha be a monotonically increasing function. And here upper Riemann Stieltjes integral, which is integral a to b bar fd alpha, is defined by infimum of u of p comma f comma alpha, and when p belongs to p of a comma b, means this can be any partition of closed interval a comma b. So here you are collecting all such u of p comma f comma alpha, means you are collecting all upper sum of each and every partition of closed interval a comma b, and infimum of that u of p comma f comma alpha will be your upper Riemann Stieltjes integral. And similarly, lower Riemann Stieltjes integral, this will be defined as supremum of L of p comma f comma alpha, where p belongs to p of a comma b. So here also this p is any partition of closed interval a comma b. So you are collecting all lower sum of each and every partition of closed interval a comma b, and supremum of that set will be your lower Riemann Stieltjes integral. Okay, so this is all about upper Riemann Stieltjes integral and lower Riemann Stieltjes integral. And now moving on to Riemann Stieltjes integral. If upper Riemann Stieltjes integral equal to lower Riemann Stieltjes integral, then we say that f is Riemann integrable. And also you have few points to note down. Okay, first one, if alpha of x is equal to x, then Riemann Stieltjes integral reduces to Riemann integration, and we denote a function f which is Riemann Stieltjes integrable as f belong to R alpha closed interval a comma b, or f belong to R of alpha if f is Riemann Stieltjes integrable. Okay, and here comes the second note. The integral value, okay, that integral value is called area bounded by the curve. Third one, the necessary condition for the function f to be Riemann integrable is f should be bounded first. Okay, that is the necessary condition. See here, this means if f is Riemann integrable, then it must be bounded. But a bounded function is not necessarily integrable. Okay, but it is a necessary condition for Riemann integrable. And here, every continuous function is Riemann integrable. And the sixth one, a necessary and sufficient condition for a bounded function f on a closed interval a comma b to be a Riemann integrable is that it is continuous almost everywhere, but the converse is not true. There are some functions that are Riemann integrable but not continuous. So a necessary and sufficient condition for a bounded function to become a Riemann integrable function is that it must be continuous almost everywhere. Then see, there are some functions that are Riemann integrable but still not continuous. Okay, now let's move on to the next concept, norm of partition. Let a comma b be a closed and bounded interval, and p equal to x0, x1, x2, etc. up to xn be a partition of closed interval a comma b. The interval a comma b is divided into n sub-intervals. So here the first one, second one, so etc. up to n. So here you are having n sub-intervals. Okay. The norm of the partition P is denoted by norm P. Okay. And it is defined by maximum of all the length. See here, x1 minus x0 is the length of the first subinterval. x2 minus x1 is the length of the second subinterval. So here xn minus 1 is the length of the nth subinterval. And you are collecting all such lengths and putting it into one set. And maximum of that set, so whichever the thing is maximum, that will become your norm. Okay. So in other words, norm P is the maximum length of the subintervals into which closed interval a comma b is divided by the partition P. Okay. as norm P tends to 0. Norm P tends to 0 means the maximum length is tending to 0. Means, what do you mean by this norm P tending to 0 means the maximum length is tending to 0 means you have more number of points. See, if you have more number of points, then there are chances of getting this maximum length tending to 0. Okay, then this u of p comma f comma alpha decreases and l of p comma f comma alpha increases. So this we have learnt in one of the note. Okay, so here as the number of points in the partition increases, then this norm p tends to 0. Okay, and by norm p tending to 0 implies the number of points are increasing in the partition. So if the number of points in the partition increases, this upper sum decreases and the lower sum increases. And now let's move on to refinement of partition. Okay, refinement of partition. If P and P star are two partitions of closed interval a comma b such that P is a subset of P star, means P star is having more number of elements and also it contains the elements which are in P. So in addition to the elements of P, it is containing some other points. So P subset of P star, then the partition P star is called the refinement of partition P. So given two partitions P1 and P2, we say that P star is their common refinement. Common refinement if P star is equal to P1 union P2. See, what is P star here? Actually, P star is the union of these two partitions, and so this P star becomes the common refinement of P1 and P2. In next video, let's start up with the theorem. So, thank you.